Chapter 4, Axial Load, Linear Change in Circular Cross-Section. So in this problem, we want to know if we have a tapered cone with the radius of R1 and R2 at both ends and handling a concentrated load at the smaller cross-section at the end of P, and the length of our system, our configuration is L, and we want to know what is the axial deformation due to axial load at a smaller cross section. Let's see how we can approach this problem. So again, if we provided with the information of a P equal to a 300 kilopounds, modulus of elasticity of system is now 9,000 kilopounds square inches. R1 and R2 are provided with the length of 10 feet. We want to know what the delta B is at the far end from the support. So let's see how can we approach this problem. So if you remember from a chapter 4, when we talk about the different kind of loading and different kind of configuration in terms of shapes, that's the video 9, which I will provide you with the link of that, but just in case, that's a number 9, and that's the YouTube link for that, and I provide that at the end of the link. It just says we have a discrete condition for delta calculation, which is separated parts like a block A, block 2, A2, block A3, and connected to each other, and we do have continuous shape. So in the first case, delta is just a summation of forces times length of that part over EI times AI. And but for the continuous condition, delta is just integration through the beginning to the end. So our case is a continuous uh, shape for our problem. It's a tapered cone, so a circular cross, a linear change in cross section for a cross circular cross section for a tapered cone. So let's see how we can uh, approach our problem. So if you just develop a whole uh, shape of a cone, and you just goes, this is our original shape, and we just extend it to develop the whole shape of the cone. And in that case, if you just simply look at the triangles, you can easily see L1 over L2. So L1 over L2, it's exactly like R1, radius at cross section 1, over R2, which is here. So you can write it in different ways. So at the same time, if we developed a sample for all element cross section in the distance of x from the origin, or the far end of our cone, it just says Rx in that case is Rx to R1 is just x distant from the origin to our element, versus over L1, which is the first cross-sectional area. So in that case, we can have an equation for R sub x, and likewise, it just gives us A sub x, which is pi times Rx squared. We do know delta for a discrete condition is just PL over EI. That's the general formula for axial deformation. And for our case, d delta, we just go for our element here. Mm. So in that case, it just gives us PL over E AX, which is a, a changing cross-sectional area through the or entire section. And that says you can integrate the equation and get the total deformation. And again, if you do so, if you just replace ax, that's which is we just show that that's pi rx squared. So that's pi. This is rx squared, which is rx is equal to what? A r1 over L1 times x. So that's rx squared and then dx. If we take the constant out of the integration and then integrate L1 over L2 dx over x squared, that just gives us a negative 1 over x from L1 to L2. Mhm. And if you replace the equation, it just gives you the 1 over L1 minus 1 over L2, which is the result of this part, replacement of that part. And if you modify that and summarize that, it just gives you L over L1 times L2. If you replace that in the equation for delta, it just gives you a delta is the constant part, which is in black, times L over L1 times L2. And that's if you just take the relation, it just gives you this equation for delta. Mhm. If you just simplify the equation, and at the same time, we do know L1 over L2, L1 over L2, the length distances are equal to the ratio of the radius. So L1 over L2 is just R1 over R2. So delta, it just goes instead of L1 over R2, L2, we just replace the equivalent value of R1 over R2. In that case, you can cancel out 1 of R1 at the numerator with the denominator, this one. So it just goes by a delta is PL over E times pi times R1 times 1 over R2. And that's leads us to an interesting result if r1 is equal to r2, if both of the radius are equal to each other, that just gives us the general equation of delta axial deformation is pl over ea, because that's pi times r1 squared, which is just the area for the first cross section or the last cross section, because it just remains the same. That's uh, if they are if we go with two different r, that's the equation. And if both of them are equal to each other, it just turns in the original equation of axial deformation. Let's put it into a practice to see how that goes. So we want to know what delta at b is due to axial force of p at the smaller cross section. So we want to know how far does the free end travels in positive x direction. Mhm. So that's again a force of a 300 kilopounds, modulus of elasticity of 9,000 kilopound square inches, R1 4 inch, R2 8 inch, twice of R1, and with the length of 10 feet over the entire cross section. So in that case, our equation from which we just calculate its PL over E times pi times R1 over 1 over R2. If we just replace our equation with the numeric value, our numeric value in the equation, that gives us a 300 over 9,000 times 10, which is 10 feet. Convert everything to feet because we have to inches because we have kilopounds, and KSI kilopounds square inches, 4 inches, 4 inches. Just convert each feet is 12 inches, and that's pi times R1, which is 4 inches, times 1 over R2, which is a twice of R1, that's 8 inches. So if you do the math, it gives you delta B, the for axial deformation at the free end is just a 0.0397 inches. Mhm. So that just gives you a delta B of zero point zero 0.03, almost zero point zero 0.04 inches. Thank you. We'll review a rectangular cross section in next video. Thank you.